This is Algebra 2 with trig, 7.6a. We're going to solve exponential equations. An exponential equation is when you have a variable expression that is in the exponents. So as long as we have an exponent that has a variable in it, that's called an exponential equation. So we have different cases. We have a case when the bases can become the same. If you can get the bases the same, then the x and y have to be equal to each other. If you have an equation that has two bases, then their exponents have to equal each other. So in this case, 5 to what power is going to equal 5 to the 4th power? Well, clearly 5 to the 4th is going to equal 5 to the 4th. So x has to equal 4. All right. So we're going to look down here at our first example. And we see that the 9 and the 27 are not the same base. They need to be the same base. So we're going to identify that 9 and 27 they can both be made of a 3. So 3 squared makes 9, and 3 cubed makes 27. So 3 squared makes 9, and 3 cubed makes 27. Now we have the two bases the same. So we're going to multiply our exponents together. So we get 4x. And we'll have to distribute as we multiply these exponents together. 3x minus 3. Then it's a nice, simple solve the equation. And we find out that x equals -3. We look at our next example. X to the 4th power. We know that 4 squared is 16 and 4 cubed is 64. So 64 can be written as 4 cubed. So that is 64 to the x power. 16 can be written as 4 squared. To the exponent of x plus 1. Now, some people might notice that 64 and 16 are also part of 2. So you could use that. You could have a base of 2, but you can also have a base of 4. So we distribute that through and we get 3x, 2x plus 2. So your x value would have to be 2 to make this equation work out. You can test it out. See how that works. 64 to the 2nd power and 16 to the power of, 2 plus 1, and those are going to be equal to each other. Love it when a plan comes together. All right, here's a little tricky one. This one has a fraction. So you should automatically know that a negative is going to be involved, because 4 to the first power, in this case, it's the first power times x, so it's just 4 to the x power. Here, to be 16, we're going to say 4 squared. That's 16. Then to bring it out of the denominator, we're going to make it a -2. Because 4 to the -2 power is the same thing as 1 over 16. 4 to the -2 power is the same fraction as 1 over 16. So it's just a good way to be able to check your work when that's appropriate. Nothing to multiply here, but here when you multiply them, you have to distribute correctly. So we have x -2x minus 6. So here we get -2.
Mr. Weber.
All right, this is case number 2. If this situation, if you're in a situation that you can't do case number 1, if that's unavailable, you can't get the bases the same. When you add the 7 across, there is no common knowledge of 6 to what power is going to equal 27. You can't break them down. You can't get the bases the same. So in this case, we're going to have to write a logarithm. Logarithms are to solve for an exponent. That's what we're doing. We're solving for an exponent. Log base 6. You have the base of 6. You're taking the logarithm of 27, and that's going to equal x. Yesterday, we learned about the change of base formula. Log of 27 divided by log of 6. So log of 27 divided by log of 6. That's going to give us 1.84. Approximately 1.84. That's approximately what x is. And we did that by using a logarithm to solve for the exponent. So here we're going to do the same thing. We're going to solve for the exponent. The exponent is what we don't know. 7 to what power equals 15? Well, 7 squared is 49. That's way too big. 7 to the first power is 7. So we know this is bigger than 7 to the first power, but it's smaller than 7 to the second power. So log base 7, because your exponential is 7, so your logarithm is going to be 7. Of 15, that comes second. That's why we go around the 15. Tells you what order to write this in. And that equals 9x. That equals the exponent. A logarithm always equals the exponent. So now we do the change of base formula. So we have log of 15 divided by log of 7. And that's 1.39 approximately. Then we're going to divide both sides by 9. So I'm still going to keep that exact number in my calculator. And I get 0.54. So that would be my value. Now we can test that value. If a calculator is appropriate, we can say 7 to the power of 9 times our answer. And since we're looking at the real answer, not a rounded answer, we should be able to get exactly the number we're expecting. So here we have 4 times e. Well, if we're going to write the logarithm, we have to get the base all by itself first. So we have to get rid of the coefficient, so divide by 4. Now you could do a decimal, 17 divided by 4. That's going to go in there 4¼ times. But there's really no need to do that. We can call that log base e of 17/4. That equals the exponent.
Mr. Weber, did you mean to bring down that x on the -2x above the e?
No, most definitely. Good call. Thanks for recognizing. We got to solve for something, right? So that's what we're solving for. We're solving for the x value. And yes, that x has to still be there. Don't lose your variables. Good job. So now log e, that's kind of weird. We don't write log e. That's not really the notation we use. So that's where the natural log of 17/4 comes from. The natural log of 17/4, that is the same thing as log e. That we can do on our calculator. Natural log of 17 divided by 4. So we get 1.45. And we're going to divide that 1.45 by -2. So remember, I'm dividing the real answer by -2. And that gives me -7, or actually -0.72 as my approximate answer. It's not the exact answer. It's the approximate answer because it's a rounded number. So now you have some here for you to try. You can pause the video, give those a try, and then take a look. Here we do not have the bases the same. There's nothing we need to do to the first base, but the second base is going to be written as 3 squared because 3 squared equals 9. And that 9 is to the 2x power. So the 7x minus 3 has to equal the 4x. So we have an x of 1. Here we have the log base 5 of 72 equals x. So log of 72 over log of 5 is going to be approximately log of 72 over log of 5. 6.66. Actually 2.66, sorry. $2.66. That is your value of x. All right, so here we're trying to solve for the exponent. So the exponent, to have a base of e, that's where we use a natural log of 3. Well, actually, it's not 3, is it? It's 3 divided by 3. 3 divided by 3 is 1. And e to what power equals 1? That's what it's asking us. Natural log of 1 is saying e to what power equals 1. So that's going to be 0. And when you divide by 0.5, you're still going to get 0. All right, this isn't too bad. We don't particularly have to do this for this year, but just to get our notes filled in correctly, we have Newton's law of cooling. we have a particular formula here that allows us to plug in our numbers. T of O is the initial temperature. T after T minutes can be represented by this equation, where T of R is a surrounding temperature, is the room temperature, and the R is the cooling rate. So we have hot chocolate has been heated to 90 degrees Celsius. It poured into a mug and was placed on a table at room temperature of 20 degrees Celsius. If the R factor is 0.145, when the time T, when is the time T measured in minutes? How long will it take for the hot chocolate to cool to a temperature of 30? So we want it to be 30 degrees. The original temperature is 90. The room temperature is 20. We have E to the negative R 0.145 times T, which we're solving for, that's your time, plus T of R, which is 20. So we're going to subtract the 20 across. And that becomes 70 to the E negative 0.145 to the T power. We're going to divide by 70. So we get 1/7. Now we have a base of E. When you have a base of E, you're going to use a natural log. We have the natural log of 1/7, which equals negative 0.145 T. The natural log of 1 divided by 7, that's negative 1.9495. That's convenient with our other negative. So we're going to divide by a negative 0.145. And that gets our T by itself. So T is in minutes. It's going to take 13 minutes for it to drop to a temperature of 30. That's just using the formula, plugging in your numbers, solving for an exponent. Here you deposit $500 into an account that pays 2.1% compounded quarterly. So we have to use compound interest. So that's our compound interest account. How long will the account take to get to 1,000? How long will it take to double? So we want to get to 1,000. You're depositing $500. You have an interest rate of 0.021. This is happening quarterly, which is 4. And we have to solve for T. So we're first going to divide by the 500. So that's going to give us 2. Our 0.021 divided by 4. And we're going to add our 1 to that. So we have our 1.00525. Now we're solving for an exponent. So to solve for the exponent, you're going to say the log of 1.00525 of 2 equals 4t. Well, that's going to be the same thing as log of 2 divided by log of your previous answer. And I believe that that was that funny decimal version. And we can divide that by 4. We get about 33.09. 33.1. That would be years. Now that's not very exciting. 33 years to double that money. Typically, when you have money that you're putting into an account, you're doing that, you're putting money in regularly. And hopefully you get a better interest rate than 2.1% on your money. All right, all we have left are some examples to hit. Nine is 3 squared. 81 is 3 to the 4th. So your exponents are going to be 4x. You're going to have to distribute your 4 through there to get 12x minus 8. All right, I'm looking back over my work to be sure that this is making sense. Okay, I see what's a little bit different from what I thought of the first time. I could have done 9 squared, but what caught my attention was 3s. So I did 3s. You could have done 9s. You would get the same answer as 1. So here we're going to have the log base 5 of 18 equals x. You would have to use the change of base formula. Log of 18 divided by log of 5. 5 to what power equals 18? 5 to the 1.8. So here we have a base of 2 of 15 that equals x. Log of 15 over log of 2. And we get 3.91. So we'll add 2. 4 e to the x equals 16. We're going to divide by 4. Now we would say the natural log of 4 equals x. That's easy enough to do on our calculator. Natural log of 4, and it is x, which is 1.39. That's approximately your x value. Here, we can't get the bases the same, so we're going to have to this would become 27. Still can't get the bases the same, so we're going to have to use a logarithm. The common log, or base 10, of 27 is going to equal your 5x plus 4. Well, log of 27, that's 1.43. We subtract that by 4. That gives us negative 2.57. And we divide by 5. That gives us negative 0.51. And that's approximately our x value. Last one, or at least for this row. So that's e to the 0.6x. That goes in there 6 times. So you have the natural log of 6 that equals 0.6x. Natural log of 6, 1.80. That goes in there that goes in there 3 times. We divide that by 0.6. That goes in there 2.99. Just about 3 times. We might as well be as accurate as we can with that. Okay, last one. All right, seem to be freezing up here a little bit. See if we can finish this off. So we get 3 to the 2x plus 1 equals 81. They're asking for 2 ways to solve this. Well, one way we can solve this is to work with the same base. So 2x plus 1 is going to equal 4. Subtract your 1 to get 3, divide by your 2, and you get 3 over 2. The other way to have done this is a log base 3 of 81. That's going to be 4. Subtract your 1, divide by your 2. So you have 2 different ways that you could solve some of the problems. You can either get your bases the same when possible. That's probably my favorite. You can use logarithms when you can't get the bases the same. But as long as you're following the rules correctly, it really won't matter which method you use. This method should always work. This method can work if the bases can match.